The last bit is IR spectroscopy, so there's no lab associated with it, but it's an important tool in food analysis, especially for online measurements and quality control assurance, identification, forensics. It's used a lot. So it's a very important tool. So your exam next Friday is going to be up until this lecture. So anything we take on Friday, Monday, and Wednesday will not be a part of the midterm. Okay? So start studying. Look at previous exam from last year. It won't be the same question. It will be the same kind of questions. Study and then try to solve them. And if you're not able to solve them, that means you did not study yet well. Go back and study. And then feel free to ask me questions. Office hours 8 to 9:30 on Friday. Sometimes I come a little after 8 on Fridays. But do email me to let me know if you want to come, or if that time doesn't work for you, we can schedule a different time. Okay? All right. Getting everybody trickling in. I thought after giving the +10, nobody will show up to lecture. But good, you're good troopers. Good. All right. So, in infrared spectroscopy, we have two main regions that we care about or are useful. So here's your visible red. Infrared is just the wavelength above the red or longer than the red wavelength. So we have the near infrared, so that means the closest to the red, and it is still relatively small or short. And then the mid-IR region, the middle, and it's between 2.5 to 15 micrometers. So now we're talking micrometers instead of nanometers. So the wavelength here are longer than the wavelength from the UV vis. And because they're longer, they carry less energy. And because they carry less energy, they will not be able to excite the atoms and the molecules on the electronic state. So you won't get electrons excited in this range. The energy is sufficient to cause vibrational energy excitation. That means bonding and stretching of the bonds. Bending and stretching. Okay, so there are different instruments and tools for mid-IR. Some are based on dispersive instruments, some are Fourier Transform, and some are reflectance, some are transmittance. So we will be talking about the different types today. And with these different types, you can do qualitative type of analysis or quantitative type of analysis. And remember, whenever we say quantitative, it has to follow Beer's law. Okay, so you have to have a singular frequency or singular wavelength to do the measurements. So we'll be focusing, as I said, on mid-IR, near-IR. The far-IR won't be of relevance to us in food analysis. So what can you come up with in terms of applications? Things I already said. Yes, Laura? Forensics. So if we're looking at identifying a foreign matter, so we look at, and I have an example later on, looking at presence of melamine in infant foods or pet foods. So you can look at the IR spectra of the infant formula with and without melamine and try to determine if melamine is present. Okay, what else? Tammy? Identifying different compounds, looking at the molecular structure of the different compound. So structure elucidation, identifying the presence of certain compounds. Quantifying. So quantification, compositional analysis. This is very powerful. Mid-IR and near-IR are very powerful tools that are used in industry to look at online composition. During processing, how does the composition change? For example, mid-IR is used, they are milk analyzers. So mid-IR is used to look at the compositional characteristics of milk as they come to, as they come as raw ingredient. So we'll talk about that later. Okay, so I think we kind of covered everything here. So qualitative detection, just looking at the presence, whether they're there, not there, what are they, looking at the molecular structure, looking at forensics, trying to identify unknown, quality assurance, compositional analysis, quantification, all of that. Okay, lots of applications. So IR has lots of benefits. The main one is non-invasive. That means you don't destruct your sample. So it's not like you're doing nitrogen analysis for protein. You put your sample in the nitrogen analyzer, you combust it, it's gone. And then you determine nitrogen here. You can put the sample through IR analysis and then retrieve it unharmed. So that's why a lot of this happens online. During processing, you can actually do measurements without having any destruction to your sample. Rapid, that is why it's quality control or quick method of analysis. It is rapid, you get analysis really quick. You don't require much of a sample preparation. Sometimes your sample will be as is, like, for example, I used to work in a flour mill, and I used to collect sample during the milling of the flour, and I would just go and run it on the IR to determine ash content. Well, the ash content is correlated with the level of bran that you have in the sample. Was it refined to the level that we wanted it to be refined or not? And then it would just, you put your flour sample in the cell, and then you do measurement right away. Not much of a preparation. However, you need to have a homogeneous sample. So if it's a solid matter, you need to be in a flour form, and the particle are of kind of equi-size and packed properly. And every time you run the sample has to be packed in the same manner to get consistent results. So it's suitable for routine analysis, it's energy efficient, environment friendly, so it's really good, cool technique. One thing I would say that I will emphasize later, if we want to do any quantification type of work, it has to be calibrated against a wet chemistry type of analysis. So you have to calibrate it against primary methods of analysis. So if you want to determine moisture content or ash content or fat or protein or whatever, you have to have calibration curves. Okay? And with the IR, you can do more than just regular compositional analysis. You can do amino acid content, you can do fatty acid content, so you can do different things, but all require major calibration against bioassays or analytical chemistry assays. So principle is pretty much the same as we've learned so far. So you have a radiation source, and then that radiation source projects your electromagnetic waves onto the sample. The different components absorb at different wavelengths, and then either the transmitted light, or we can also learn about reflectance of light. Either the transmitted light or the reflected light gets to the detector, and then you get a spectra. Okay? And the spectra is unique. The IR spectra of each compound is so unique, different, because of each functional group will absorb light differently, will have different vibrations. Because of that, you have a very unique IR spectra, kind of a fingerprint, again, for every type of molecule. So this is just to remind you that the vibration or the energy associated with IR are equivalent to vibrational energy that is allowable within each molecule. And it's quantized, not continuous. This is just a reminder of our intro to spectroscopy lecture. And you can see here the energy that is electronic is not achieved within vibrational energy. The transitions are within vibration energy that are less of energy than the electronic energy. So they're here. So this is 0, ground state to the first vibrational level, second, third, fourth, fifth, and so on. You do not get enough energy in the IR region to get you to the higher level of electronic energy. Okay. So again, the same principle, the IR radiation, same as UV and visible radiation, you also look at frequency, and frequency is associated with the energy. The higher the frequency, the higher the energy, and the H is Planck's constant. So it's the same with any other type of radiation. Oftentimes you see that the absorption spectra or transmission spectra in IR is not against wavelength, it's against wave number. So instruments and the computer systems in IR usually gives you the plotting of transmittance, reflectance, sometimes absorption, against wave number rather than wave okay? And wave number is basically 1 over wavelength in centimeters. So that is the so it's the unit is centimeter, the -1, basically, of a wave number. So what happens when the molecule absorbs IR radiation? You end up having a vibration above its regular vibration at the ground state. So these vibrations are due to stretching and bending of the bonds. So these are just a little animation on this is stretching. You have symmetric stretching. That means the atoms within a molecule are going and stretching in one direction. And asymmetric is when they stretch in opposite directions. Bending is any bending of the bonds, and also it can be in plane, out of plane, and different types of bending. You don't have to worry too much about that. But anyway, so there are different types of stretching and bending, and from there, when the molecule absorbs the light, it goes into this higher vibration state, and then when it releases, go back to ground state, it releases its stretching and bending, basically. It restores to its original vibrational state. So again, there is only allowable vibrational states, so it only absorbs the radiation if it's within its allowable vibrational state. Okay. Okay. We're back. We're back in business. We're back. Okay. This is a typical IR spectra in the mid-IR region. So here's a compound, butyraldehyde, and then for each functional group can vibrate and bend at different wave number. So you can see here the vibration and with specifically stretching of the CH bond, and then you have stretching of the carbonyl and C double bond O. So each one of these have different wave number at which they can vibrate or absorb energy. And you see here it's downward. This means in this region here, the y-axis is percent transmittance. The more you have, the more concentration of a certain functional group you have, the less transmittance of that wave number you're going to see, because it will be the energy is absorbed at that wavelength or wave number. So you will see a lower dip. So then the percent transmittance will be lower. The lower the concentration of certain functional group, the higher the transmittance. So the transmittance is for any the wavelength that were not absorbed, or the energy that was not absorbed would be transmitted. And that's what the IR is measuring. It's measuring percent transmission. And then, like I said, the y-axis, the x-axis is not necessarily wavelength, it's wave number, and the unit is centimeter to the -1. So it's very characteristic of this compound. So it's really an powerful identification tool that we can use to identify different compounds. So it's qualitative. You can do it as qualitative measure for a strong identification tool. So in different compounds, you have different functional groups, and each have absorbed at different frequency or wave numbers. So you have the alkanes, for example, measuring the CH stretch and bend, or the methyl, the CH2 or the CH3 bending. And same with like aromatics, have a different functional groups that would stretch, alcohols, and so on. And this gives you the frequency at which these bonds would vibrate. Okay, so it's very characteristic. They are known in literatures. That's why we can use them as strong identification tool or structural elucidation, because we know their wave number, we know what they are, so we can actually piece together the information and gives you structural identification of different compounds. Can IR be employed to measure mineral content in atomic absorption? Think about it, all of you. Will? You said yes? Are you sure?
Certain.
You're certain?
100%. I'll make a dance band.
A dance now?
Are you just gonna like be your
Okay. Why are you certain?
For the conversion to remove the organics and the bonds that are organic between carbon.
Well, not necessarily carbon and hydrogen. You have other different types of, you can do inorganics too with IR. The point here is with atomic absorption, you are measuring absorption the atomic state. So gaseous atomic state. So there are no bonds involved in that analysis or technique. With IR, it's based on absorption of energy by the bonds that result in change in the vibrational state of that molecule. So no, we cannot use IR for using atomic absorption from the name atomic. So we cannot. So here you see a little bit of detail in certain like radiation source, detectors. You're not really supposed to know all of this. They're just here for FYI, but I want to explain the difference between dispersive instruments, for example, and then FTIR coming up next. So in dispersive instrument, that means the light is dispersed. It's dispersed into singular wavelength. So you do have a monochromator in your instrument, So it disperses the light into individual radiation or wavelength or frequencies and sequentially pass them through the sample, so one after the other. And then you get a spectra at all of the different wavelengths. So you do get them separated, and then you get a sequential analysis. Okay? The components within the instrument are similar to that of the UV vis, and often it's double beam. That means the beam is split between a reference cell and a sample cell. However, dispersive instruments are no longer in use. There might be old ones in your lab or what have you, but they don't usually, are not usually used anymore. The more common one is the Fourier Transform, or what you have probably heard of is the FTIR, Fourier Transform infrared spectroscopy. So they're more complex instruments, and a lot of different calculations. It's called Fourier Transform calculations to convert the radiation into IR spectra. In this case here, you don't have dispersion of light. All of the light hits the sample, and then the sample absorbs at the different wavelength, and all of these wave absorption or transmission or reflectance of light, we'll see that there are different forms, will get used and converted to a spectra using highly function mathematical calculations. So in this type of instrument, there is an interferometer. So that means there is interference of light. So if you remember the amplification cancellation from the introduction, so I told you we will come back to it in IR. So what happens here is your light source gets split and then gets projected to different mirrors and then re-intersected together to amplify or reduce the power of certain wavelengths or certain frequencies. So you can amplify or reduce the power. And this increases the sensitivity and increases the specificity of the method of the detection or the spectra or the fingerprint of your analyses. So, and improves the signal to noise ratio. So it's highly sophisticated instrumentation compared to the dispersive instrument. So you can measure transmission or you can measure reflectance. So transmission is mostly when you have liquid sample. So then your light goes in, and then whatever is not absorbed goes out, gets transmitted. So it's mostly for liquid sample. If you want to use solid samples, you can, but then you have to pack it with potassium bromide or disperse it in a mineral oil. Then the light can be transmitted through, and some molecules can absorb part of that light. So attenuated total reflectance, that's usually used for solid, paste, or really viscous liquid. So here the light hits the surface, and then it gets reflected, but that goes in for a little bit, and the molecules in there absorb some of that light, and the rest of the light that did not get absorbed gets reflected, and that projected to the detector. And then the detector can calculate the difference of the light that was absorbed versus the light that got reflected. So internal reflectance can be used for liquid samples. So liquid samples can also be used in reflectance. So the light goes in for a little bit, a few micrometers into the liquid, and then interacts with the molecules in the liquid. Some molecules absorb some of the light and then reflect. The rest of the light is reflected. So there are several interfaces with the IR. You can actually use gas chromatography linked to IR. So the IR would be your detector in this case. So you get your separation, and then the IR would be your detector. And you can have a microscope, which is really cool. You can have your specimen on a slide, a thin specimen on the slide, and you project the light through the microscope, and then you get a scan, and you scan the surface on a very thin specimen that you have on your slide. This can be applied to look at, let's say, crystallization on the surface of a sample. I think one time I invited somebody from General Mills to talk about this, and she talked about something cool they do with sugar-coated Cheerios. So they actually measure the crystallization of the sugar on the Cheerio using this tool to look to see if the crystals are uniform across the surface of the Cheerio. It's pretty cool. We can do quantification, whatever, but you have to have Beer's law being followed. That means we measure at a unique or specified frequency. So mid-IR milk analyzers are very commonly used, and they are used to determine the major constituents. So fat, we look at carbonyl groups, the absorption of carbonyl groups. And for protein, we look at absorption of the amide groups. And then lactose, we look at the absorption of the hydroxyl groups. And we can do that simultaneously, but the sample has to be homogeneous and also pumped through into the flow cell. We use this instrument, like I said, after calibration. So it has to be calibrated. Usually they calibrate it by using Muginer, because it is dairy. So they use Muginer method, which you will learn about next week. So they will use Muginer for fat. Oftentimes they use Kelda for protein, or nitrogen analysis method, the DUMAS. We'll learn about that as well. And for lactose, they measure lactose also using either total carbohydrate assay or an enzymatic assay specific for lactose. So they measure those in samples that are prepared with different concentration of these different components. And then they will kind of have a standards built. So actually, I used to take the food analysis group to a lab that analyzes milk samples. But at the time, I only had 18 to 20 students in the entire class, so they were able to accommodate us. But now they won't accommodate 40 students. It'd be a lot to get you into the labs there. So I stopped doing that field trip. But they would show us how they actually prepare the milk samples. They actually reconstitute milk samples with different concentration of protein, different concentration of fat, and lactose, so that they can build their own standards. And they run them with the analytical assay, and then they calibrate their IR instrument accordingly. So the newer mid-IR or milk analyzers have FTIR as their actual instrument. So they use the Fourier Transform calculation to get you more accurate results and faster results. And the way they do that, they take absorption at multiple wavelengths and they apply multivariate regression to get you the concentration. It's pretty sophisticated, but as an analyst, you really don't need to know all of this detail of how the instrument works, as long as you know that you need to build the calibration and you need to have a bare minimum understanding of how to read the spectra and what it means. This is for later, for you guys to study from. So Raman Spectroscopy is another cool IR. I've used it in research actually, so it is highly sophisticated and also gives you very cool information, strong information that tells you changes in molecular structure once you apply certain processing. So it really is very sensitive and can detect structural changes. So what is Raman spectroscopy? It's really based on scattering of a photon of light. So we have what is known as wavelength scattering and then Raman scattering. The Rayleigh scattering is that when a light hits or a sample, a molecule, so the molecule gets excited, and then when it gets back to the ground state, it releases a photon of the exact same energy. And that gets scattered, and that's what Rayleigh scattering is. However, some molecules, when they absorb light, they release photons of light that are of a larger or a longer wavelength or lower frequency, and they go back to not the baseline of their vibration state, they go back to a little higher vibration state. That energy that gets scattered has, as I said, lower frequency. So then this is called Raman scattering. So the scattered photon has less energy than the incident light. Well, this is too technical. It can observe symmetric vibration, not just asymmetric. So that is detailed information. But what I want you to know is the source of light is laser. You can use it for quantitative analysis. But then you have to do that at specific frequency. And you can use solid and liquid samples. So in IR, mid-IR, and near-IR, water absorbs IR. So it can get can mask some other functional groups. In Raman spectroscopy, water does not absorb, does not scatter light. So there's no interference from water, which is really good. Spectrum is less complex, relatively less complex. You just have to be trained in understanding the spectrum. So moving on from mid-IR to near-IR. So these are instruments often used for compositional analysis of any type of food. You can use it on solid food and minimal sample preparation. And often you use what is known as diffuse reflectance technique. So you have your solid material and you pack it in your cell. And then you have the light source or the energy source projected towards your sample. Some of that light or electromagnetic wave gets reflected, but there is no detector there because that light that is reflected has no signature or chemical signature of your sample. However, the remainder of the light that does not get reflected goes in and interacts with the different molecules, and the different molecules absorb some of that energy. And then the energy that is not absorbed at different wavelengths is reflected at a different angle. And you position your detectors, you have usually multiple detectors to capture all of the reflected light. So, and usually they're projected at 45 degrees angle. So then the light that gets reflected carries the chemical signature of the constituents. That means the light that gets absorbed is absorbed, and the remainder of the light that does not get absorbed get reflected, and then that's what you use to do the calculations and produce the spectra and identification of your sample. With that, you have to control particle size and shape, use thorough grinding, because the particle size and the shape affect the reflectance. So you really want to be careful there. Absorption bands in near IR are overtones and combination. That means they are broad peaks. They're not sharp peaks like mid-IR. So oftentimes you have to do deconvolution of the peak by mathematical calculations to remove overlays. So the measurements on near IR is basically the functional groups that have a hydrogen atom attached to carbon, nitrogen, or oxygen. These are the common groups in water, proteins, lipid, and carbohydrate. So these are the main constituents. So water, we look at the OH stretch, protein, we look at the amine deformation or stretching and bending. You can see this happens at multiple wave numbers. So it's not only one particular wavelength number, it can happen at multiple regions. And then the lipid is the methylene, and then CH2, CH3. Also, this happens at different wave numbers. And carbohydrates, CO and OH stretch, and this happens over this particular range. So if we look here, for example, so we have the cheese sample, wheat and egg white. So both wheat and egg white are low in moisture and then low in fat. So here you have really large peak around the 15,000 nanometer. So this is because of the high moisture content. Here in this region you have the fat, and here you have mostly your protein. So you can see that, and then some water too. You can see, because you don't have lots of water in wheat, you can see the actual peak for protein without an overlay of the water peak. So radiation source is near IR, tungsten halogen lamp with quartz envelope. Quartz does not absorb in that region in the near IR, it absorbs in the mid IR. You can have either a monochromator or interferometer. Often you have the Fourier Transform technology, and then different types of detectors. Again, FYI, nothing to worry about here. So you can measure reflection or you can measure transmission. Reflection is mostly for solid samples, have to be packed tightly. You can use a quartz window for your cell. Quartz does not absorb light in this region. Or you can use transmission, and this is for liquid samples. Again, you place them in quartz cuvettes and measure absorption at different wavelengths. Finally, you can do quantitative analysis. Again, it's based on mathematical calculations and regression using different wavelengths. So you use multiple linear regression analysis. You run your calibration, and then you can identify unknown in your sample. If you look at applications, this is the example where I showed you that you can do forensics and look at a pure melamine, which is contaminant that was added to infant formula to add the nitrogen content to falsely value that it has higher protein. So, however, the melamine IR spectra is very unique. If we run an infant formula and you run melamine, you can see that there are differences. So if you have melamine contaminating an infant formula, you will see specific regions that are specific for melamine. So you can detect the presence of that. Otherwise, if you do nitrogen analysis, melamine is high in nitrogen. And that's why if you just determine protein based on nitrogen, it won't tell you if it has melamine in the sample. So near IR is used a lot in grain and cereal products, oilseed processing. So it is an approved method, AACCI approved method, but again requires calibration. For dairy products as well, a lot of these products include butter, cheese, milk, whey powder. So yes, we said that already. It can be used online measurement. It's quick, fast, non-destructive. That is why. So there are lots of advantages and disadvantages. So you can read that on your own. And that would be the end of that. We are 7 minutes early. Shall we start proximate analysis?